Hello and welcome back to ECMath. This is the second video in our video series on inverse functions. In the first video, we looked at how to define f and f inverse and compare if two functions are inverses. And we also looked at a procedure for computing the inverse of a function. If you haven't yet viewed that video, I'd really recommend you see that one first. I'll put the link down below. So the second video is going to be more about the theoretical background of inverses and some stuff about domains and ranges and things like that. So first, let's start with just a really neat fact about a function and its inverse. If a function has an inverse, and not all functions do, then the graph of f inverse is the reflection of f of x over the line y equals x. So here are two examples. F of x in the first is in red, is a linear function. If you take a line and reflect it over a line, you get another line, but with a different slope. And they meet at just the single point where y was equal to x. It looks like the point 1, 1. The second pair of functions, we had g of x was maybe some kind of square root function, maybe the square root of x minus 3. And it looks like g inverse of x here is x squared plus 3. And you'll notice that those two functions are complete reflections of each other over the line y equals x. That's just a really neat fact. And of course, the reason is in the inverse procedure. Remember, in the inverse procedure, we tell you to exchange y and x. Well, what do you think that's going to do to a graph? It's going to take all of the coordinates that you might have on a graph, say this point is x comma y, and when you interchange them, it's going to map that to some other point, y comma x. So of course it's going to flip your line over the graph y equals x. And it's just a really nice relationship. As an aside, I will say every year I get a couple students who think they're really, really smart, and they think that they could just ignore everything in the first video and find inverses by somehow drawing a reflection and then finding the equation of the reflection from the graph. And I will say, that might be you right now, thinking you're really smart and that you can do that. In theory, yes. I have never once seen that work in practice. I would really recommend you go back to that first video and learn how to find inverses using algebra. All right, so fun fact out of the way. Now here's one of the main ideas of this video. Determining if f has an inverse. So it is true that every function kind of has an inverse relationship. That is, most operations and functions can be undone in some way. And you can always switch x with y and at least try to solve. But not every function has an inverse that is also a function, or that is well behaved or works the way we expect it to. And it is, of course, nice to know when that is going to happen. Like most of the examples in the last video had nice inverses that we were able to solve for. And that brings us to something called the horizontal line test. It goes like this. If any horizontal line passes through the graph of a function more than once, then the inverse relation of f will not be a function. Sometimes this is said that f has no inverse, but I'd rather say that f inverse is not a function. So let's check this out. Horizontal line passing through, well, the horizontal line will only hit a line one time, which means that no matter where I draw that line, every x maps to just a single y, and every y maps to just a single x. So this, we'll say f inverse exists. Let's look at the second one, though. Downward facing parabola. Here's a horizontal line, and there are situations where a horizontal line would only hit this once, but in this case, we're going to say that we'll pick the line to be here at, I'll say, some y value, and this does hit the function twice. So there's some x1 and then some other x2 that both map to y. So it is fair to say, of course, that f of x1 is equal to y, and f of x2 is also equal to y. But, and here's the big difference, and this is why we have the horizontal line test. If I did have an inverse, and I said, okay, what's f inverse of y? Well, that would be saying, go backwards and tell me what x I started with. And I can't do it. It's either x1 or x2. So in this case, the inverse relationship is not a function. Y is a function of x, but x is not a function of y because this has failed the horizontal line test. So we'll say f inverse does not exist, or it's not a function. Let's try this again. Third graph. Oh, this really fails. So for some given y value, for this y value, I actually have 3 x's. That gave me that single y value. So if I was trying to travel backwards for the function, figure out what x gave me that one y, I would not be able to answer that question. So f inverse, again, does not exist. Fails the horizontal line test. But you don't have to be just a single boring line to have an inverse. Lots of functions have inverses. So in the last example here, we can see that this function actually does pass the horizontal line test because we have 1y going to 1x. So f inverse exists, and it passes the horizontal line test. Also remember from way back when, a couple weeks ago, that we had this thing called the vertical line test. That tests if y is a function of x. The horizontal line test tests if x is a function of y. And so they're different tests, and it can be confusing, which test to apply where. The vertical line test just tests if you're looking at a function in general. Horizontal line tests confirms that you have an inverse that's also a function. Here's a piece of mathematical vocabulary for you. So say you have some function f of x. If f of x first is a function itself, which means every x has only one y, and that it passes the vertical line test, and f of x has an inverse that is also a function. That means every y comes from only one x, and it would pass the horizontal line test. So the function in our third example above, something like this, is one such function that passes both tests. Then that function is called a one-to-one function, because no matter how you say it, every x gives you exactly one y, and every y gives you, or correlates with, I didn't do that very well, every y correlates with exactly one x. And that's why we call it one-to-one. That's a really nice piece of vocab that will show up a lot if you continue on in your math studies. And just as a quick aside, we can think about functions as ordered pairs. We could say this is f of x and this is g of x. Which of these functions are one-to-one? Pause the video and check it out and see if you can figure it out. I've turned this into a mapping diagram to help look at this. We've just converted the ordered pairs, the x and the y, the x and the y. And we can see from the mapping diagram really clearly that this function on the left is not one-to-one because we need every y to map with only one x, as well as every x to map to only one y, and these three arrows going to just the value of 1 is a big problem there. On the other hand, this function is one-to-one, because even though we have these repetitions, -7, -7, those are x's and y's, so every x goes to exactly one y, and if you turn those arrows around, every y goes to exactly one x. And that's a one-to-one relationship. So to close this video, we're going to talk about what is probably the most technical and tricky thing about inverse functions, which is restricting the domain of a function so that it does have a well-defined inverse. It turns out that even if a function fails that horizontal line test, sometimes we would like to construct its inverse anyway, just because it's really nice to be able to undo the action of some other function. So if you do have a function that's not one-to-one, but you wish to construct its inverse, you must restrict its domain to a specific part that you're going to find the inverse for. Let's look at an example. All right, so in this example, I started with the function y equals x squared minus 1. And I ignored the horizontal line test, even though I can see that this function clearly fails the test. I just ignored it for a minute. And I applied the standard inverse finding procedure. I wrote y equals x squared minus 1. I switched x with y. And I started trying to solve for y again. So I added 1 to both sides. And then I square rooted both sides. But when I square rooted both sides, I had to put a plus and minus on that root. And when I went to graph this in Desmos, I was not able to graph that as a single line. I had to graph the positive version and then separately the negative version. And that's the big clue that the inverse relationship, it was not a function. Now, if I just checked my horizontal line test ahead of time, I would have figured that out earlier. But, such is life. That said, I was certainly able to graph the top half of that, and I was certainly able to graph the bottom half of that as perfectly good and reasonable functions. I could even say, maybe I just only want to graph one piece or the other piece of this. Maybe I could have an inverse in some way. And that's what we're going to do down here. Before we get started, please make note of this key idea, which is that inverses interchange x and y. So the domain of f, whatever it is, will become the range of f inverse. And the range of f should become the domain of f inverse. And as we do this, we're going to actually list the domain and range of each. That's a key idea, and if you're asked to find domains and ranges for functions and their inverses, you can use this idea even if you're not applying the idea of domain restrictions. You can use it for all functions and their inverses. But let's get going on here. So what I'm going to do is take my original graph, x squared minus 1, and I recognize that this totally fails the horizontal line test. But if I selected just a portion of it, say the left portion, that's strictly increasing, this part passes that horizontal line test. So I'm going to add a little domain restriction to my function to say for x greater than 0, I'll define f of x to be this way. And basically I'm crossing out the other half of my function. I'm only looking at the right half of this parabola. Now let's apply that procedure to find the inverse. So I'll write f of x equals x squared minus 1, but I'm going to write the domain restriction in every line. Now I'm going to write it as y equals x squared minus 1. And now I'm going to do the key step of interchanging x with y. So I write that x equals y squared minus 1. But I'm also going to interchange x with y in that domain restriction. Key idea. I'm going to put a big star by this. Interchange that x and y in the domain restriction as well as the function. And now I'll keep solving. X plus 1 equals y squared for y greater than or equal to 0. And now we'll take the square root, and I'll square root x plus 1 equals y. And in the last example, this is where I had to put a plus and minus on here. But this time, I have this statement that y is greater than or equal to 0. And so I don't actually put a plus or minus on here, because since y is greater than or equal to 0, and the square root of x plus 1 is equal to y, I'm going to choose just the positive version of this function, and that's going to be my f inverse. So for f of x restricted in this way, f inverse of x is the positive square root of x plus 1. And let's list some domains and ranges too. I'm going to list them in sort of a little T-chart. So for f of x, the domain was we chose x greater than or equal to 0. And just looking from the graph, the range was y greater than or equal to -1. Now for f inverse, the domain becomes the range and the range becomes the domain. So for f inverse, we'll have the domain x greater than or equal to -1, which makes sense because we're looking at the function square root of x plus 1. So we do in fact have that domain, that x can't be anything smaller than -1, or we'd be taking the square root of a negative. And we have the range y greater than or equal to 0. And if I go ahead and graph the square root of x plus 1 on the same axis, let me cross that out. Remember, that's a shift of the graph of square root. So it'll look like this. It'll look exactly like that using what we know about square root graphs. Shifted to the left one, no stretches, no nothing else. And we also have the idea that these are reflections over y equals x of each other. Next half of the example. My choice of the right side of that function was completely arbitrary, and I actually could have chosen just as easily the left side of the function. So let's see what would happen if I had done that right now. So I'm imagining sort of crossing out the right half of the function, choosing the left half, and that will give me the domain restriction x less than 0. So now if we rewrite f of x, it's x squared minus 1 for x less than or equal to 0. Rewrite that as y equals. We switch x with y. In the domain restriction as well, and continue to solve. But when I get to this step, earlier I would have had to put the plus and minus on here. However, I have this restriction that y is less than 0. So I'm only going to write the negative part, since my restriction was y less than 0. And now I have the inverse function created. So we'll write f inverse of x is equal to negative root x plus 1. I can graph that as well, so what would that do? That's going to be the square root graph, shifted over to the left, but then instead of opening upwards, it's going to open downwards. Actually travels over many of the same points. Actually, I should do that in a different color. Let's do that in like blue. There. It's going to travel over many of the same points and go out this way. So that's f inverse of x. In this case, where our f of x was the negative half of that restricted graph. So your inverse will depend on what domain restriction you choose of the original f. But once you've chosen a restriction that is one-to-one, you can solve, and indeed you can successfully find an inverse. For the last problem of the day, we're going to put it all together. So let f of x equal x minus 1 quantity squared. We first need to restrict the domain of f so that it has an inverse, find the inverse, give the domain and range of both, and then graph both on the same coordinate plane. All right, well, I know it says to graph last. I'm going to start by graphing at least a sketch of f first so that I can understand what a one-to-one interval might be for this function. So it's a parabola, right? Squared gives you parabola. X minus 1 means shifted to the right. And it goes over 2 and up 4, and over 2 and up 4. So it should look something like this. And now that I've seen the graph, at this stage I kind of have to pick. I could either select the right half of the function to restrict to, or I could pick the left half of the function to restrict to. I don't know. I'm feeling kind of right-handed today, so I'm going to pick the right side of the function to restrict to. I'm going to cross out the left half of the function. Now the right half of the function started at 1, so I'm going to restrict the domain to x greater than or equal to 1 And that will be my interval piece of the function that passes this horizontal line test. If I chopped off any less of the function other than that whole left branch, it would not pass the horizontal line test for its entire space. So here's my function. Now with the domain restriction intact, let's go ahead and apply the inverse solving procedure. We're going to find that inverse. Switch x with y. Square root. I'm going to keep the plus or minus on there. And I'll add 1 to both sides. We'll say 1 plus minus root x is equal to y. But I have this domain restriction that y is greater than or equal to 1. So since y is greater than or equal to 1, if I go over and look at the plus and minus, I need y greater than or equal to 1, which means I can't be starting with 1 and subtracting anything. So I need to take away the minus since the y needs to be greater than or equal to 1. So really, my f inverse is just going to be 1 plus root x equals y. That's going to be my real f inverse based on that domain restriction I had. So we'll write that. F inverse of x is equal to 1 plus root x. And again, I know I said list the domain and range of both, but I have the thing. I'm going to go ahead and graph it before I list the domain and range. I'm going to go over here on the same graph. I'm going to clear off that left half of the graph that I restricted away. And let's graph f inverse on the same coordinate plane. So this is the square root graph, but it's shifted up 1. So we'll start at 1, 0, and then make that shape of the square root graph. Clean this up a little bit too. Actually, let's do this in a new color. Do that in purple. There we go. Over 4 and up 2. So here's f inverse of x. Here's f of x, at least for those specific domain restrictions. And we can list the domain and range of both. We can kind of do this in a t-chart again. So we have f inverse, the domain, and the range. So the domain of f was what we chose. We restricted it to be x greater than or equal to 1. And the range just from the graph was y greater than or equal to 0. For f inverse, I can either look at the graph or I can just use the idea that these are swapped with each other. Either should give you the same thing. Looking at the graph, I can see that the domain is x greater than or equal to 0, which is exactly the range of f. And I can see that y is greater than or equal to 1, which was exactly the domain of f. And that's how you kind of bring all this together in one go, right? We've restricted the domain, we solved for an inverse, we graphed them both, we found the domains and ranges of each of the results. And that's it, folks. That's all there is about inverses. The only thing you have to do now is practice. Let me know what questions you have. Good luck on your homework, and I'll see you all next time.